right. Well, it's 1 o'clock, so time to get started. How's everybody doing? Did you get outside yesterday? What'd you think? Oh, can you hear me? Can you hear me? Abdul says yes. Yeah, okay. Can I hear you?
Hello.
Hello.
Ah, okay, good. I can hear you. Yeah. All right. Well, let's get started. Today we have two main topics. We're going to talk about salinity, and we're going to talk about inorganic carbon, carbon dioxide, things related to carbon dioxide, and pH, which in lakes is very strongly connected to inorganic carbon. We are now entering the chemistry, the lake chemistry part of the course. And for everything that we talk about in this part of the course, we really want to learn eight things, right? So the first thing we want to learn about these different chemical topics that we're learning about, so this week's salinity, for example. So with respect to salinity, the first thing we want to know is, what is it? What's the definition of salinity? What is it? We want to know why it's important in lakes, in lakes in particular. We want to know what different forms it can take. If we are talking about a chemical element like phosphorus, we want to know what different forms does phosphorus take in lakes. If we're going to talk about inorganic carbon, not only, what is it, but what are the different forms of inorganic carbon? So that's what I mean by forms. Solid, liquid, gas, this molecule, that molecule, dissolved, solid, different forms. We want to know how it is measured by limnologists. We want to know what kind of equipment and materials do they use to measure it, and what units are used to describe it. We want to know what pattern and process. We want to know what are the different processes that affect its distribution within a lake. Does it diffuse? Is it carried by moving water? Is it stratified? Is it, what are the things that determine where you find it in lakes and in what abundance? Obviously something like photosynthesis that consumes carbon dioxide is going to affect the carbon dioxide distribution in a lake. Where there's lots of photosynthesis, there will be less carbon dioxide available. Where there's lots of respiration, on the other hand, there's going to be a supply of carbon dioxide, and so there might be a higher concentration there. So that's an example, these like that affect every one of these things that we learn about. Today, salinity, inorganic carbon, and pH. Now we also want to know not just what processes affect it in a lake, but also what's the distribution? Where do you find high salinity and where do you find low salinity? Where within a lake do you find high pH and where within a lake do you find low pH? And what time of year? So, and what about different lakes? Are all lakes the same or are different lakes different? And if different lakes or water bodies are different, how are they different? How is a really deep stratified lake different from a shallow polymictic lake? And how is that different from a wetland? How is a meromictic lake different from a holomictic lake? So we want to know how does this chemical, whatever it is, how is it different in distribution among different lakes? What's the pattern? And I think the final question is some of these things some of these chemical topics, these water chemistry topics, sometimes there's just something that's just straight out interesting about it. something that attracts attention, maybe something mysterious or unknown, or something that is the subject of active research right now or recently. And, you know, it might not be something that fit up here into the category of like, it's important, but it's something that people talk about or think about, the limnologists would know about. And so, you know, if you got a job working with a limnologist and, you know, they mention something that's limnologists find interesting, you know, it'd be good if you knew what they were talking about. So that's kind of this last one. So these are the kind of the big 8 things that we want to learn about each of the chemicals that we're learning about in the next, well, for the rest of the course. So for the rest of the semester, we are now in the water chemistry unit. This week, carbon dioxide, salinity, and pH. Next week, oxygen and redox potential. And the week after that, nitrogen, phosphorus, and maybe a little bit about iron. I gotta check the calendar here. Yeah, and then the final week of class, everything else. Phosphorus, nitrogen, those are the big ones. Iron, that's a smaller topic, but has some important aspects to it. And sulfur, which is of an increasing interest recently. And so that's your kind of your big picture. What do I need to know? You know, what do I need to know about oxygen? This is what you need to know about oxygen. What do you need to know about phosphorus? This is what you need to know about phosphorus. You know, so that's kind of to give you a sense of what the big picture is on these things. This is fairly close to the order in which CALF covers topics within the chapters. And I think that pretty much everything you need to know is in the textbook. Pretty much almost everything. And I'm also going to cover a lot of it in lecture as well. And not surprisingly, a lot of it you have probably learned already. In chemistry class, for example, everybody's taken general chemistry. And environmental science students who took environmental chem, I don't actually know what is taught in environmental chem. They have had different people teaching it, and nobody's actually talked to me much about the topic since I designed the course in the beginning, like 5 years ago, but other people have been teaching it ever since. So hopefully you've learned good things there that will help you. But it's not a prerequisite. If you're a biology major and you're just coming in with a chemistry background, you know, you'll be fine. We'll teach you everything you need. All right, so let's start out with salinity. And let's see, I have some PowerPoint slides. And if you like PowerPoint slides, okay, that didn't work. I just posted it on D2L, or a version of it. So you can, you know, follow along on your own screen or your own paper or whatever works for you if that's something that you do. All right, so our first big topic of today is salinity and lakes. And we just copy and pasted this in here a moment ago. So why is salinity important? Oh, should we answer our first question first? What is salinity? Well, salinity is the weight of all dissolved ions. It is not just sodium and chloride. Salinity is the weight, the density, you know, the weight per volume water of all dissolved ions. Now, there really are actually 8 ions that dominate salinity in natural waters, and often salinity is said to be the sum of just that 8. Or it's the sum of all of them. And since the 8 is most of them, those are pretty close together when you measure them. So it's not just sodium and chloride, right? It's all of the dissolved ions, particularly calcium, magnesium, sodium, and potassium, right? Those are your big natural cations. And then carbonate and bicarbonate, chloride, and sulfate. Those are the big 4 ions. And I'll show those to you on a slide in a moment. So that's what salinity is. Salinity is the dissolved ions, particularly the dissolved inorganic ions. And, the true units of salinity are going to be, mass per volume, milligrams per liter, for example. Well, why are we starting with salinity? Well, because it's like probably the most important one, really, right? It's kind of it's what they call a master variable. The salinity really affects everything else. It's not the only thing that affects everything else, but it's one of those things. So it's really important. That's why we're starting with it. So here's a graph from Calf, and this is just giving you an example of how important salinity is. I mean, as you know, there are freshwater fish and there are marine fish, right? There's freshwater algae and marine algae. There are freshwater plants, not many, but some. And there are marine plants, very few. And they're different. In all of these cases, they're different. They're freshwater zooplankton and marine zooplankton. They're different species. So that's kind of what we mean by a master variable. If you're going to compare water, freshwater lakes at one end, the ocean pretty far over here, and then saline lakes or even saltier over here, you're going to see completely different species in freshwater than you see in saltwater or a saline lake. But it's not just which species, it's also how many different species, like the diversity. So this is a graph from the textbook showing you the macrozoobenthic species richness in the littoral zone. So big animals associated with the littoral zone, attached things. So we're talking about things like dragonfly larvae, or well, I think amoebas are not macro zooplankton, zoobenthos, so they'd be micro. Snails, clams, leeches. So big animals that are attached animals and live in the littoral zone. So littoral, macro, zoobenthic. Species richness, number of different species. And what you can see is on the x-axis, as salinity increases, the number of different species goes down. Species richness declines with increasing salinity. Now, this axis is a logarithmic axis, and this one is also logarithmic. So, here we've got 1 species, 2, 3, right? So these numbers are 1, 2, and 3 species. And up here, these numbers are like 20, 30, 40 species. So if you can picture, these lakes here have like 10 times as many different species as these lakes. The x-axis is also logarithmic. So these lakes here have a salinity of about 100 grams per liter. That's a lot. That's saltier than the ocean. And these lakes here have a salinity that's like 10 times the salinity of these lakes here, which have about 10 grams per liter. And you'll remember that the salinity of the ocean, of seawater, is about 35. So 10, 20, 30. So here, seawater would be in here. So this is a wide range of salinity from very, very low salinity, very fresh, to very saline. And in Saskatchewan and Alberta, they have a lot of saline lakes, as we also do in eastern North and South Dakota. So they really have a wide range of salinity in the lakes that they can make a graph like this. Okay, and now Kelf points out to you, you know, you can't really tell what the shape of this is. Mentally, I think it's hard to visualize. So here's a little cartoon of the shape, I think. But they're showing, notice this rapid decline between 3,000 and 10,000 milligrams. And so that's between 3 and 10 grams. So here we have 1, 2, 3. So in between here and like here, you know, where it drops from like 20 to 10 species. So big drop off. Then you get down here and, you know, because these numbers, because it's logarithmic, this is gentler than you can picture. So shaped like that. Okay, anyway. So salinity is a hugely important variable. It really determines which species can live in a particular environment, in a particular lake, you know, ocean versus freshwater, right? But also when you start getting up into salinity above the salinity of the ocean, when you start getting into real high salinity, boy, the number of different species completely drops off. You get up to high salinity and there are very few species that can tolerate such a high salinity. So the units on this graph, right? We got grams per liter of salt, and this is what they call total dissolved solids, TDS. And if it dissolves in water, it's probably ionic in some way, at least partially ionic. So another way to describe salinity is as the total dissolved solids. And the way that you would measure this is you take a liter of water and you evaporate all the water. You evaporate the water off so that anything that was dissolved is left behind. And then you get this like powder on the bottom of the beaker, and you weigh it. If you took a liter of seawater and evaporated all the water, you would have a beaker with 35 grams of salt in it, primarily sodium chloride, because it's the ocean. So that's what these units are, and species richness is simply the number of different species. Okay, so that's a kind of a long explanation of how important salinity is. Now let's return to this question of what salinity is. All right, so salinity is the sum of ions dissolved in water. And what are those ions? What particular chemicals are they? Well, this is showing a bunch of different sets of lakes from around the world. Here's an overall world average. Let's start with that. And what you can see is that when you look at all of the anions that are dissolved in water, the most abundant anion is bicarbonate. And then the second most abundant one that accounts for maybe about 20% of the total is sulfate. When you look at the cations dissolved in your average freshwater lake from around the world, what you see is that about 10, 20, 30, a little over 30% of the cations are calcium ions. And, you know, I'm not sure what that would be, about 15% on average magnesium. And then, well, I don't know, that's a little bit less than 10%, but, you know, something about 10%. Certainly number 3, they've got sodium and potassium. Now, it's not exactly the same thing in different parts of the world. This is sort of a worldwide average of, you know, moderate to low salinity lakes. But if you look at particular groups of lakes around the world, like Sweden, you can see Sweden has maybe more bicarbonate and a little less sulfate. You look at, in contrast, Western Norway, and if you think about Scandinavia, see what direction are we looking here? Okay, my hand's reversed. I'm not sure which way you see it. Anyways, if you look at far Western Norway, that's the part that's close to the ocean. And you look at, it goes Norway, Sweden, you know, Finland. And so then you go to the east and you get farther away from the ocean. If you're on far Western Norway, which is next to the ocean, there are lakes there, you see a much higher fraction of the anions are sulfate. Yeah. And maybe a bit more of the cations are sodium. Okay. Whereas if you go to, there's a bunch of lakes in Sweden, right? So we got different groups and they're all more dominated by bicarbonate and calcium. I think Minnesota's on this list here. Is Minnesota here? Anybody want to make a guess for me? In this group of Minnesota lakes that was studied, what was the dominant anion and what percent was it? So look at this and tell me, in this group of Minnesota lakes, what was the dominant anion and what was its percent, approximate? And also what's the dominant cation and what's its percent? So look at this graph. It's also in your book. Try to read this graph and then make a guess and put it in the chat. And we'll see how you do. So this is a graph reading thing, but this is also an important factoid. So. So what's the dominant anion and what's its approximate percentage? And then what's the dominant cation and what's its percentage? Lots of people are weighing in and everybody's right so far. So lots of agreement. How about the cation? Yeah. Yep. Good. All right, good work. Good work, people. So we're looking at Minnesota lakes and we're seeing that the dominant anion is bicarbonate. And this doesn't have the little pluses and minuses on it, but bicarbonate has a single negative one, a negative charge 1. And that's maybe 80%, maybe a little over 80%, maybe even 90%. And then dominant cation in Minnesota lakes is calcium. And how much is that? 20, 40, 60, looks like more than 60, but less than 80. So 70 sounds like a good guess. And of course, you know, it's not got your plus and minuses sign on it, but calcium ion has a 2+ charge. Now it's typical to express salinity in terms of grams per liter, but some of the methods for measuring it just lump them all together and use their charge to measure them. Like, how well does it conduct electricity? You know, the more ions in the water, the better it conducts electricity. So you can just measure how well the water conducts electricity. And from that, you can infer the salinity. Well, when you do that, you can't really tell the difference between, you know, a whole lot of things that have a +1 charge versus like half as many ions with a +2 charge. And some things with a plus charge, you know, and some things with a equal charge are different masses. So you can't really infer exactly the milligrams per liter just based on the conductivity of the water. But you can convert it to an estimate of how much calcium and bicarbonate would be in the water. if it had that conductivity. And when you do that, then this is called equivalence or milliequivalents per liter, meaning we measure the conductivity. If that conductivity was entirely from calcium carbonate, how many milligrams per liter of calcium carbonate would there be? So essentially it has a salinity that is equivalent to this much calcium and carbonate. And since calcium and carbonate are by far the dominant ions, that's going to give you an answer that's pretty close to the actual milligrams per liter. But not literally, so they don't call it milligrams per liter, they call it milliequivalents per liter. Now there's some tricky math involved and we're not going to go into the details, but I think you know that different atoms have different masses and different ions have different charges. And that's the source of the tricky math that we're going to just skip. There is a footnote or maybe even an appendix. I think Professor Kalf might have an appendix explaining it if you want to go into detail. Okay, so why are some lakes dominated by some ions and other lakes less dominated? In other words, why are these Western Norway lakes, why do they have so much more sulfate and sodium compared to, Minnesota lakes or even Swedish lakes? Well, there's a couple of different things that contribute to the salinity. And one of them is chemical precipitation. So the ocean is not dominated by calcium carbonate. The salinity of the ocean and many salt lakes of similar salinity, the ocean and many saline lakes are not dominated by calcium carbonate. They're dominated by sodium chloride. And why is that? Well, the big reason is because sodium chloride is much more soluble in water. You can put as much calcium carbonate as you want into water, but if you just got regular old water at the surface of the earth, nothing special, no pressure, no, other elements in there, no, weird pH, just like ordinary surface water, you are never going to be able to dissolve more than about 10 milligrams per liter, 1/100th of a gram per liter. And I typically do this in the classroom, but I didn't bother to bring all this stuff home. But you can do this. You can take a liter of water, and you can grind up chalk, or just get some calcium carbonate from the chem storeroom upstairs, and just look and see how much chalk can you dissolve in water. And once you've dissolved everything that's going to dissolve, if you put more in, this is going to fall through to the bottom. And if you dissolve more in the water by like warming the water up or something, so it dissolves better, and then you cool it down, if it cools down below that saturation, it'll precipitate out. So calcium carbonate is not very water soluble. You really cannot dissolve, practically speaking, you really can't dissolve more than 1/100th of a gram per liter. You can put in as much as you want, but you're not really going to get more than 0.01 grams per liter staying dissolved in the water. If you keep adding calcium, it might stay in solution if there's sulfate in the water too. And calcium sulfate, which has the common name gypsum, is more soluble than calcium carbonate. With gypsum, you can get up to like 2.5 grams per liter dissolved in water. But you try to put any more than that in and it's going to precipitate out. Now, sodium sulfate, that's another combination of elements. Sodium sulfate is a salt. It's called Glauber's salt. And there are some saline lakes that precipitate glabrous salt around the edges. And it's a useful thing. It's similar to, there are some lakes in Africa that precipitate glabrous salt and similarly related ones. It's related to the salt that the Egyptians used to mummify mummies. You know, I mean, it has some obscure, but anyways, it's more soluble than calcium sulfate, a lot more, and you can dissolve up to like 140 grams. But all of those are much less soluble than sodium chloride. So if you've got sorry, if you've got water flowing into a lake and it's bringing with it calcium and sulfate and sodium and chloride, like it's bringing in all of those ions. And let's say that it's a closed basin lake. So water flows in, bringing stuff from the watershed. Doesn't have to be very concentrated, just regular water flowing in with ions in it. And then water evaporates out. The concentration of the ions in the lake itself is going to go up and up and up and up. So the ions wash in from the watershed. The water evaporates out, leaving the ions behind. If you have a lake where there's more evaporation or equal evaporation to the inflow, there might not be any water flowing out of the lake at all. We call that a closed basin lake. If you have a lake that gradually becomes more and more and more concentrated over time, the first thing that's going to happen is calcium and carbonate are going to precipitate out together. They're separate, right, at first because they're ions dissolved in water. But if there's calcium ions and carbonate ions, and the concentration gets too high, if they bump into each other, they'll bind to others, and then suddenly you've got a little snowflake of calcium carbonate, and it just falls out. Once all the calcium carbonate has precipitated out and the concentration in the water continues to rise, calcium bumping into sulfate is going to bind and precipitate and form a solid. Once the calcium sulfate is mostly gone, then you're going to start to see sodium sulfate precipitating. And finally, you'll be left with mostly just sodium and chloride. And there are lakes that have so much evaporation that even the sodium and the chloride precipitate out, and you get deposits of salt, table salt around the edges. So over time, you expect the balance of ions in a lake to change. If a lake is becoming increasingly saline because of evaporation, you will see things evaporating, see things precipitating out, forming a solid in a sequence. And over time, what you see is that calcium forms solid salts that precipitate out first, leaving the sodium behind. You see that the carbonate precipitates out first, leaving the sulfate and chloride, and then the sulfate will precipitate out, leaving the chloride. So you see this gradual change over time in the nature of the chemical composition of the salinity in a lake, if the lake is becoming more and more saline. Well, the ocean has been around a long time, and you know, water doesn't flow out from the ocean anywhere. You know, the oceans of the world are all connected to each other, and there is no out. Water doesn't flow out from the ocean anywhere. So over time, the ocean has gotten more and more salty, more and more concentrated, to the point that the dominant thing that's soluble is the sodium chloride. Now, you could make the ocean a lot saltier and it would still be dominated by sodium chloride, right? Because the salinity, the solubility is much higher than what you see. And when you look at very salty lakes, like the Great Salt Lake of Utah or the Dead Sea, as it's called, they have a way higher salinity than the ocean, but they are still dominated by the same two ions, sodium and chloride. Okay, this is both an important process that affects the composition of salinity, and it's also just a really cool thing about lakes. Minnesota has one lake that is a natural saline lake. It's called Salt Lake, and it's near Marietta, Minnesota, which I'm willing to bet no one's ever heard of. It's kind of out past Lac qui Parle. It's south of Big Stone. It's right on the border to South Dakota, North Dakota. It's near the North and South Dakota border, and it's on the border of Minnesota with the Dakotas. And then if you just cross over the border into whichever Dakota that is, there's a whole bunch of small saline lakes out there. And they draw an unusual bird population in the winter. They're kind of famous birding locations. And the one that's in Minnesota is a scientific and natural area, I think, of the Department of Natural Resources of Minnesota. So they're protected, but they're funny because they're just kind of surrounded by fields, you know, and it's a very shallow lake, and it's got like a white crust on the mud around it from the precipitated, they would call them evaporites. All right, I don't have a lot of slides, and I'm not going to say this much about all of them, but I wanted to really describe this to you in detail because in my experience, this is something that no undergraduate knows coming into the class. And in fact, many environmental science graduates don't even know it. So I feel confident that you've all learned something if you listened. So do you have any questions about this? Does this make sense to you, what I have explained? You have all taken chemistry more recently than me. So, you know, I hope that this somehow connects with chemistry that you've learned and makes sense thinking chemistry thoughts. So give me a show of hands if this makes sense to you. You know, you can give me a check mark. If you're like, it makes no sense to you, or for whatever reason you weren't paying attention, you could give me an X. If this is like exciting and interesting, you can give me some kind of hand gesture. You're like, nobody thinks this is exciting and interesting, really? Aww. I think I have just done a remarkable job explaining something that actually most limnologists do not explain clearly. You could take a whole class, you know, you can take a whole graduate school class in lake salinity if you wanted. It's like cool equilibrium chemistry and stuff. Oop, okay, all right, well, let's move on then. Let's look at some lakes and let's see, what's our question? How does it vary? I think we've mentioned how it is measured, right? Milligrams per liter. If you assume that a liter of water weighs 1,000 grams, if 1 liter of water weighs 1 kilogram, then you can translate grams per liter into parts per thousand, PPT, parts per thousand. Now, parts per hundred is percent. Parts per thousand is PPT. Parts per million, ppm. Parts per billion, ppb. We will use those units in this week, next week, and the week after. But just remember the conversion between the parts per unit is based on the assumption that 1 liter of water weighs 1 kilogram. So if you have 35 grams of salt in a liter, that's 35 parts per thousand, 35 grams of salt per 1,000 grams of water, 1,000 grams of solution. Yeah, okay. All right, so some basic vocabulary words. Fresh water is fresh water. Fresh water is drinkably fresh, right? It's got a salinity less than 1 part per thousand, less than 1 gram per liter. That's fresh water. At the other extreme is brine. Brine is very salty, and brine has a salinity above 50. And brine, you know, that's the word like pickle brine. Like if you were to pickle vegetables by packing them in salt water, salt pickles, you use brine. So we're not talking about a vinegar brine, we're talking about a salt brine. In between, slightly saline is the term brackish. Saline, that's salt water, and then brine. So saline is, you know, seawater fits in the saline range. Most saline lakes fit in the saline range, 30 to 50. Slightly salty, that's brackish. Very salty is 50. Okay, so if you look at this table here, I would like you to tell me, you know, the Great Salt Lake of Utah, which of these 4 terms, which of these 4 words best describes the Great Salt Lake of Utah? Freshwater, brackish, saline, or brine? So which of these 4 words best describes the Great Salt Lake of Utah based on the information in this table? And once you've got that answer, you know, what's the dominant ion, what's the dominant anion, and what's the dominant cation in the Great Salt Lake of Utah, according to this table? So first question, what word describes the water of the Great Salt Lake? And then what's the dominant cation and what's the dominant anion based on the information in this table? And I'm going to pull up my little annotate tool in case this is all visually like you're like, what? Okay, so here we go. Here's the Great Salt Lake. There we go. All right, looks like everybody's getting the answer right here. It's brine, because we got 332. That's really salty. That's like almost 10 times as salty as seawater. But it's true that seawater varies a bit from place to place, and so does the salinity of the Great Salt Lake. It rises and falls, and it's different in different parts. So I think it would be safe to say, yeah, it's like 10 times as salty as the ocean. And you might be predicting, sodium chloride, therefore. And what do you see? The dominant cation, well, biggest number here is sodium. Dominant anion, biggest number, chlorine. All right, there are some other famous salt lakes here. You know, we got the Dead Sea. Right above that, we've got Mono Lake, which is on the Nevada-California border, which is a very cool lake. They thought they found, was it 2 or 3 years ago, 5 years ago? It was in all the newspapers. Somebody found life there that seemed to have arsenic in place of phosphate in the DNA. And there was this, for some reason, some newspaper reporter thought that meant life on other planets might have DNA with arsenic instead of phosphorus. I don't know what the logic was there, but there were these headlines about, you know, life on Mars has arsenic, you know, or something. And it was, I'm like, what? And I had just been to Mono Lake recently. Anyways, it's a very interesting lake. The only reason it's so salty is because it's on the other side of the mountains from California, or from, you know, the population of California, and they built a pipe. And they diverted all of the snow meltwater to Los Angeles. And then with no water coming in, the lake just dried up. You know, it just got shallower and shallower and shelter and saltier and saltier and saltier on these like great big pillars of salt, and calcium carbonate pillars were depositing. And you can walk on this board. You should go there. you can walk on this boardwalk out into the, what used to be the middle of the lake. And there's all these like little mummified seagulls. So when a seagull dies and it falls on the evaporites, it's so salty that they don't decompose. They just gradually mummify. Anyway, so it's like eerie. I don't think it kills the birds. I think it's just the birds die, but then they never decompose. And you walk out and there's like stuff lives in the water, like one thing. Okay, it's maybe three, but like one thing, some kind of brine shrimp. So it's weird. It's got this weird smell. It's a very, very otherworldly. You should go there when the class is over and, you know, COVID's gone and all that. Anyways, there are other salt lakes. Soda Lake is the famous one. Van Lake in Tasmania? Okay. I think that you can see that when you look at the lakes that are not nearly as salty, and these are arranged in order of kind of increasing salinity. So let's pick one that's kind of near the base of the pyramid here. Well, let's just take this one that's only, would you even say this was saline? No, you would, how would you call this lake? Redberry? What term would you use to describe Redberry? And what are the dominant ions in Redberry Lake? So what word would you use to describe it? And what are the dominant ions there? Yep. So this lake is brackish based on its total salinity. And the dominant cations are magnesium is the number one. And the dominant anion is sulfate. So farther down the salinity scale, different ions are dominating, just as predicted. Okay, I will clear all of my drawings and close and move on. Okay, where are the saline lakes of the world located? Well, here is the western edge. Oh, where we go? Oh, here's Minnesota here. Here's the western edge of Minnesota. And I think I mentioned there's a large area in which there are many saline lakes across the border into Canada in the Great Plains and then up into the Rocky Mountains. So British Columbia has a bunch of saline lakes. People I know have worked in British Columbia. Alberta, Saskatchewan, in here. And then, you know, just that far western edge of Minnesota into the Dakotas over there. Mono Lake is here. I think number 5 is Mono Lake. Here's a zone in Nevada. You can go to Nevada and there's lots of saline lakes there. It's like a local specialty. There are some other patches in North America, South America, about which I don't know as much. And of course, there are many saline lakes in this area. It's very dry, right? There's water, but the water tends to evaporate. So salts get concentrated. And you may not be aware that a large area, the large central area of Australia is desert, very dry grassland, and there are a lot of salt lakes, saline lakes there. So here are the areas in the world that have a lot of saline lakes. And in North America, not such big areas, but areas that we know and care about. So why is that? You know, you're going to find salt lakes where there's liquid water, it flows in, but it evaporates faster than it evaporates at an equal rate to the rate at which it flows in. So whatever the basin is never fills up and spills over, right? So we call that a closed basin lake. It's not really like it's closed, like, you know, it's under a roof and sealed, you know, with a door, but it's more that there is no outlet. Now, if a lot more water flowed in and nothing evaporated out, it would probably fill up. And everything, you know, has an outlet if the water level rises high enough. But if there's so much evaporation that it never gets that high, it is effectively a closed basin. This is from a paper by Evel Gorham, Professor Gorham at the University of Minnesota, quite a while ago, actually. I'm pretty sure this is what he was the source of this paper. And this is showing the distribution of lakes of different salinities in this kind of 5-state region. Now the unit here is the micromole. The micromole, and that is the measure of conductivity. So if you were to measure salinity with a conductivity meter, and the better it conducts electricity, the higher the salinity. The unit of conductivity is the mho, M-H-O, which is, should I write that out for you? So the unit of conductivity is the M-H-O, or the, or the millimole typically. And that is ohm backwards. Get it? Because ohm is the measure of resistance. The ohm is a measure of electrical resistance. And so the mho is the measure of electrical conductivity. So they called it the mho. Okay. I know it seems like it's sort of like a nerdy joke, but it's serious. Anyway, so up here we have greater than 7,078 micromoles, between 500 and 7,000, between 140 and 500. So this is very low conductivity, and all the way up to very high conductivity. And so you can see that the various saline lakes, this is where they're located. I don't know what is in this patch here. I don't know any lake in here that is salty. That doesn't mean it isn't. I swear I don't know any salty lakes in here, but maybe there are. Anyways, the one I'm talking about is right here. Yes, on the border with South Dakota. And there are a patch of salty lakes here and up here. If you want lakes that are not like truly salty, but just kind of a bit towards the brackish side of things, there are quite a few, and they're over here. One exception over here, I think this one is a mine pit lake, which is not naturally saline. You get to lower and lower and lower conductivity, and you can see they're more distributed like that. So in case you like to travel and you want a picture of the upper Midwest, here's a map showing a distribution of lakes of different salinities and where they're kind of distributed within the 15,000 lakes we're talking about. Okay, so how is the salinity distributed? Here is a map kind of showing you big picture, a difference in salinity between different lakes. Now, the number one cause of salinity for lakes is evaporation exceeding precipitation, meaning rainfall. If evaporation exceeds rainfall in the watershed, that's when you're going to start seeing saline lakes. If you're going to start seeing grassland instead of forest, it means there's less precipitation, less rainfall. If you start seeing desert instead of grassland, it means there's even less effective rainfall. So that ratio between water coming in and water evaporating out is what's going to determine whether a lake in general is saline or not. Okay, I'm going to clear my drawings. Oh, in there. Oh, look, I put in a little arrow. There's Salt Lake, Minnesota. All right, how can you predict, without ever going somewhere, if lakes are going to be salty, if they're going to be brackish or saline or even brine? Well, it's really kind of about the ratio between rainfall, precipitation in the meteorology sense, rain, water falling from the sky, the ratio between water falling from the sky and water evaporating. Although water evaporating is determined by temperature. So what we have here is a graph of the world with the average annual temperature of a place on the x-axis and the average annual precipitation, rainfall, water in centimeters on the vertical axis, on the y-axis. Now, Minnesota, our average annual temperature in the Twin Cities area is about 50 Fahrenheit, which is about 8 Celsius, right? And the average annual rainfall is about 78. So Minnesota is up here, like Minneapolis is like up here. Now you go out to North Dakota, to Devil's Lake, North Dakota, and the temperature is a little bit colder. It's near Fargo. The temperature is colder, but the rainfall is much less. So Fargo is going to be like 6 degrees, like here, and less rainfall, so like here, down here near 50. So you can see that on this diagram it's showing for the Minneapolis weather, the annual climate here, we're really at the low probability for having closed basin saline lakes. You get up to that Fargo, and now you're talking a higher probability. You've run across this line, and now you're more likely. Now, what about Pierre, South Dakota? Can you tell me which kind of zone of this map is Pierre going to be in? Is it going to be in between the 0 and the 50, in between the 50 and 100, in between the 100 and the 150, or in between the 150 and the 200? So which of these zones is Pierre, South Dakota, going to be in? Anybody got a guess? Or which of these lines is the closest to? Yeah. Looking at my chat here. Jeff, anybody chatting? Okay, Drew's got a guess here. Anybody else? Where is Pierre, South Dakota going to fit on this chart? So 8.5 degrees Celsius for the average annual temperature, 51 centimeters for the average annual precipitation. So that's going to put us, somewhere 51, 8, somewhere in this area here. Actually not that far from Fargo on the graph. So you can see Devil's Lake, which is in North Dakota, is in that same zone. So are the Salt Lakes of Saskatchewan in the same zone here. Mona Lake is down here. Salton Sea, oh, here's the Dead Seas over here. Where's the Great Salt? They don't have the Great Salt Lake here. Yeah. Okay, so there you go. There's Minneapolis, there's Fargo, and there's Pierre. All right, any questions about this? Reading this graph, or it's kind of right, the x-axis and the y-axis are pretty clear, and then you've got these kind of hand-drawn lines on it, which mean things, yeah. Okay. All right, where does the salinity come from? Salinity is ions. Salinity ultimately comes from rocks. Now, chemical weathering of rocks in the watershed is the number one source of salinity for lakes. Now, we're talking primarily about sedimentary rock. And the way that the chemical weathering works in brief, is you take carbon dioxide in the atmosphere, you mix it with water in the atmosphere, and you get a concentration of carbonic acid. Now, H2CO3 is the combination of CO2 and H2O. And H2CO3 dissociates. It tends to lose one of its extra hydrogen ions, one of these protons. It doesn't hold on to its protons very tightly. It tends to lose one of them. And because it releases protons into water, it is an acid. That's the definition of an acid. An acid is a chemical that when you put it in water, it increases the proton concentration of the water. It increases the concentration of hydrogen ions that are available to do stuff. So CO2 plus water makes a weak acid, carbonic acid. Now the rule for rocks is that soft rocks make hard water. By soft rock, we mean like limestone and sandstone and shale, sedimentary rocks, rocks that are made out of ocean sediments from long, long ago. By hard water, what we actually mean is water that has calcium carbonate in it. Obviously, calcium is a dominant ion in salinity, and so is magnesium. But when you have a lot of calcium and or magnesium in the water, it's pretty easy to exceed the solubility limit. And when you do that, you get calcium carbonate precipitating. People don't like calcium carbonate precipitating in their pipes. They don't like it precipitating, in their bathtubs. They don't like it precipitating, right? It's this sort of gray, chalky, muddy looking stuff. And water that is hard water contains a lot of calcium and magnesium, up near the saturation limit. So when people get a water softener, a lot of times what they're trying to do is remove the calcium and the magnesium from the water, because they don't want this stuff precipitating and gunking up their pipes. And it makes it, soap doesn't work very well in hard water with a lot of calcium and magnesium in it. It tastes funny. Actually, there isn't really anything else wrong with it. I mean, it's perfectly healthy, but people don't like it. Okay, so the rule is soft rocks, meaning sedimentary rock, dissolve and release calcium and magnesium and carbonates into the water, which makes the water hard. I know this is like fancy technical terminology here. If you're from whatever, Minnesota or Iowa or something, maybe super familiar with these terms, but if somebody's from a different part of the world, this must seem really weird vocabulary. Okay, so carbon dioxide, natural component of the atmosphere, dissolves in water, forms an acid. Natural rainfall is slightly acidic. Perfectly clean rain is slightly acidic. It dissolves sedimentary rock and contributes ions to the stream flow that runs into the lake. That's the number one source of salinity for lakes. The number one source of dissolved ions is the dissolving of sedimentary rock by clean rain. Now, there are some other sources of ions to lakes. And that goes into a formula like this, based on the geological grouping, as you see in this formula. So the area that I grew up in, one of the areas I grew up in, had salt springs. The local theater group was the Salt Spring Playhouse. The nickname for the city I grew up in is Salt City. And, back in the Erie Canal days, the dominant industry, or a big industry, was the production of salt. And the reason is because their mountains are pushed up like this. And there were some salt beds in the rock that, because of the geological tilting, brought them near the surface. And so there were actually salty spring water in some places. There are some places where lakes are really, really deep and cut into a bed of salt. And so they have a source of salt, like sodium chloride, that comes from old ocean sediments. That's unusual. It's special. But it's possible, it happens. If you're downwind from the ocean, in fact, you will get extra sodium and chloride and sulfate deposited, just because every time a wave crashes, a little burst of drops are thrown into the air, and they often evaporate. Well, if you take water droplets and throw them up in the air and evaporate it, the salt is left. The salt was carried up with the liquid water drop, and if the drop evaporates, the salt is in the air and gets deposited. It can get deposited in mist, so wet fall, or it could be just dry dust and little particles. So these are some of the other sources of salinity to lakes. Igneous rocks contain have a different elemental composition than sedimentary rock. And very calcareous, crushed up rock like glacial deposits, not only are they sedimentary rock, but they tend to release their elements very easily because they're already crushed up and broken, and they have lots of surface area and so on. So here's a formula, just based on empirical data, predicting the conductivity of lake water, and it predicts it pretty well based on three things. The amount of runoff per year, the area of the drainage basin, and the type of rock in the drainage basin, the watershed, the drainage basin. Okay, so if you go to a bigger number for the geological grouping here, 1, 2, 3, the bigger number is going to give you more ions going to the lake and a greater total conductivity. If the watershed area is bigger, if W is a bigger number, then the natural logarithm of W is a bigger number, and that's going to increase the conductivity. Runoff, on the other hand, so the amount of rainfall that doesn't evaporate is rainfall, is runoff, capital R, runoff. And you can see that as runoff goes up, if R is a bigger number, the natural logarithm of R will be a bigger number, and that makes the total conductivity go down because it's negative. So you can predict, at least sort of generally with some accuracy, the conductivity of the lakes in an area, like the average conductivity of lakes in an area, based on these three factors. The climate, the size of the watershed, and the type of rocks in the watershed. So I hope this makes sense to you. And if it doesn't, Professor Kalf explains it. Okay, so what are the things that affect the salinity of lakes? Drainage basin area, rock type, and the climate. And those are the three things in that formula. Biota, the living things that are on the landscape. If there's a lot of vegetation on the landscape that holds the soil well, it'll reduce the ions that come in. If, on the other hand, you have things like pine trees or sphagnum, plants that acidify the soil, that's going to increase just by making it more acid. That's not like one of the big three, but it's in the top 10. Soil age. If rocks are young, like less than a couple thousand years, they have a lot of minerals that will dissolve. If the soil is old, if the rock is really old, like 1 million years old, everything that can dissolve has dissolved. They don't have a lot of soluble minerals left. So young soil contributes more to conductivity. Young rock contributes more to conductivity than old. So Minnesota, young. Mexico, old. Sea spray and inflow from the ocean can contribute sulfur, sodium, and chloride. As I've described, if you've got sea spray that evaporates, you can have ions, sodium and sulfur come in particular. Also, if you're near the ocean and not that far above it, like there might be big tides that every now and then bring seawater into a lake. And there are lakes that go back and forth between being freshwater and being kind of brackish, because whenever there's a really high tide, they get seawater in. Acid precipitation from human activities like fossil fuel combustion can be a source of ions to lakes. Nitrogen and sulfur, for example, come from gasoline, not nearly as much as they used to, but that is still a significant source of nitrogen and phosphorus to the air. And mercury, of course, comes from coal combustion, and so does sulfur, comes from coal combustion as well. Humans put salt into the environment. Road salt is a big source of salt to lakes in urban areas. And fertilizer also contains salt. Despite what you may have heard about salting the earth, actually salting the earth in some circumstances fertilizes the earth. It's not actually generally a plant killer historically, unless you're putting the kind of levels that we do with road salt. Yeah, so there's something a little complicated in there, but certainly ammonium, which is put on fields as a fertilizer, is a salt, ammonium. I mean, it's an ion, it dissolves in water. So fertilizer it's not a top 3, but it's in the top 10 for sources of salinity to lakes. And volcanoes, you know, they evaporate rock, right? Melt it and evaporate rock. So they can be like a weird source of weird, unusual ion fluxes downwind. And this is another graph that shows you a lot of what I've said sort of in a diagram form. I don't know if this diagram is going to work for you or not, but you know, give it a try. What we've got here is the salinity is the vertical axis. Brine is at the top. Fresh water is at the bottom. So it's kind of freshwater, brackish, saline, brine, right? So the saltiness is the vertical axis. And then the left to right axis is which is the composition of the salinity. So on the left, we have calcium bicarbonate. What dominates freshwater down here. Over here is sodium chloride. So you see this great big sort of diagonal pattern in this chart. Very low salinity lakes are typically dominated by calcium and bicarbonate. Very salty water, there's nothing here. There's nothing in this upper left-hand corner because there are no lakes up here. If you are this salty, you can't be this salty with calcium carbonate. So anything that is this salty is going to be dominated by sodium chloride. So there's kind of this big trend that's a diagonal, and you know, an absence of anything up in the top left corner, because that just can't happen. But below that kind of zone where you reach the solubility limit, you can have a mixture of different, you can have a variety of different salts dominating. For example, you could be basically a freshwater lake, but you're near the ocean, very near the ocean, like downwind from the ocean. And in that case, you might be fairly freshwater, but kind of dominated by sodium and chloride. That would be over here. Precipitation, meaning rainfall, dominated lakes that are near coasts. Low salinity, but kind of towards the sodium and chloride spectrum. And in between here, we would have like those calcium sulfate and sodium sulfate, you know, those other salts in between. So, you know, you could peruse this diagram at your leisure and see if any of it makes sense to you. You might find that it helps you see the big picture, or I don't know, it might not. It might not. It's my opinion, this diagram works for some people and not for others. So here we have precipitated dominated lakes, like rainfall dominated lakes down here. Here we've got kind of rock dominated lakes in a large area. And then up here we have like seawater and truly salty things up in the upper right. Yeah. Okay. So that is what I have to say in my little PowerPoint about salinity. So I'm going to stop sharing and see if you have any questions. And I'm going to look at my notes and make sure I said everything that I wanted to say. Where my notes go? Say anything I wanted to say. Salinity tends to be uniform within lakes, generally speaking, although it can be higher in shallow areas of a lake where there's a lot of evaporation. If a lake has sort of a deep basin and then shallow bays, it may be more saline in the shallow bays. Of course, meromictic lakes, the bottom water, the monomelymnion, is generally speaking always very saline. There we go. All right, any questions about salinity? Questions, comments?
Yeah, can you just re-summarize why it is that sodium chloride is the main ions in very saline lakes compared to like Minnesota lakes where a lot of the ions would be calcium carbonate instead?
Well, it's because it's the most soluble. So, I mean, let's say seawater has 30 grams per liter of salt in it, right? Sodium chloride, mostly. So let's say that you took a liter of water, and into that liter of water, you put whatever, 35 grams of calcium carbonate and 35 grams of sodium chloride and 35 grams of magnesium sulfate. Cover all my big ones, right? So you put all of those things in there. What's going to happen? The calcium and the carbonate are going to precipitate out. The sulfate and the magnesium are going to precipitate out. And you'll get magnesium carbonate and calcium sulfate. Like those things, they'll all bind together and precipitate out. But the sodium and the chloride will stay dissolved. So why is the ocean dominated by sodium chloride? Because the concentration of salts in the seawater is 35 grams per liter, which is far, far above the saturation limit for the other salts. The seawater probably holds as much calcium carbonate as it can hold. Like it's maxed out. It is holding as much calcium carbonate as water can hold. But that's not really very much. Seawater can actually hold more sodium chloride than it does. It has not reached its limit. But that limit is much, much higher than the limit for calcium carbonate. Does that answer your question?
Yes, thank you.
All right, other questions, comments about salinity? You feel like you got these 8 things answered? If you feel like you got these eight things answered, yeah, with a little bit of studying, yeah, haha. You know, give me a check mark. If you're like, wait, those 8 things, I didn't hear you mention any of them. Give the X mark.
What about if you have something in the middle?
Yeah, I'm more in the middle right now.
Like, I'm like, I can answer a few of them, just not all of them.
All right, let's take a survey. There's 8 things on the list. How many of them do you think you got? Like, or pretty close to, or maybe. So how many of these 8 do you have? How many of these 8 have you learned? Just put it in the chat. We'll just look down a list of numbers and get a sense. Like a 4. If they're numbered, you could count them too. 4, maybe 3. What? 3? 4. People are locking. Are there any of these in particular that you didn't get that you want me to explain?
I think it's like more towards the end, like the last few ones.
The pattern of distribution? Yeah, I didn't really talk about within lakes very much.
Yeah, I think 5 through 8. I think Catherine's right. 5 through 8 or more, the ones that I do not get as much.
Well, what is it that affects the distribution within a lake? You know, it's really just evaporation. But lakes tend to be really well mixed. So for a holomictic lake, there's really, generally speaking, the salinity is the same everywhere. If you have, in contrast, a meromictic lake, and you'll remember that a meromictic lake, we didn't talk about this as much as I usually do, but in a meromictic lake, even when the lake is mixing completely, it doesn't mix all the way to the bottom. In a meromictic lake, this part, the upper part of the lake is called the Limnology. And the bottom part of the lake here is called the Limnology. So this is a meromictic lake. And a meromictic lake never mixes all the way to the bottom. It's the opposite of a holomictic lake. The thing that makes a meromictic lake meromictic, well, there could be a couple of different things that start it. But what happens is, if in the springtime it doesn't mix all the way to the bottom, and then it doesn't mix all the way to the bottom in the fall, then it's going to be anoxic down here, no oxygen. That's going to cause things to dissolve into the water from the sediment. And then this water becomes denser and denser. And then because it's really dense, it's even harder for the wind to mix it. And then it becomes more and more likely that it's not going to get mixed. Now, it typically, almost always, a meromictic lake is pretty small surface area and pretty deep. Really deep relative to its surface area. And the surface area is where the wind gets the energy to mix it. So if it's a small surface area, there's not a lot of wind energy blowing across, or whatever. There's not a lot of ability for the wind to get the water moving. And if it's really deep, it's hard for the energy to get down to the bottom to move the water. So meromictic lakes are pretty much always relatively small surface area, relatively deep. They don't need to be a giant lake, although there are really, really big meromictic lakes. It can be really small or really big. But the thing is that relative to its area, it's really deep. So Brownie in Minneapolis is a meromictic lake. Now, a lake could be right on the border in terms of its dimensions, but if it's near the ocean and some seawater flows in, then you could have salty water at the bottom, and that could just kick the whole thing off. Because it's salty, then it's hard for it to mix. If it was barely able to mix it to the bottom, and now there's salt water down there, then it can't. Or if you have a fairly deep, small lake that's getting a lot of road salt, so that there's a supply of salty water that could kick it off. So there's a couple of different things that can get it started. But one of the dominant features of a meromictic lake is this bottom water that never mixes. And this water is always saline or deeply enriched with things dissolved from the sediment and stuff. Okay, yes, Jude.
For that equation that you showed us, that total salinity equation,
Yeah.
For the geological groupings, those were like the, I think, igneous, sedimentary, and calcareous, right?
Yeah.
Okay.
And that equation is from Calf. It's in the textbook with some explanation. All right. So hopefully that is explaining a little bit more about the distribution within a lake. It's really distinctive for something like a meromictic lake, but also something like a salt lake. You know, if you have a very shallow lake that's saline and it's got a little bay that's very shallow, that little bay might evaporate down to practically dry. Well, that little bay is going to be very saline. So when you look at a map of the Great Salt Lake of Utah, there are several bays, and in a satellite photo, the bays can be different colors because the salinity is different, and there's different algae living in the different bays because of the different salinities. And it probably doesn't always look really cool, but sometimes there are, you know, pictures from space that you can see that just make it, that they're just really cool. So yeah, if you have a big lake like that and it's got a bay that's shallow and another bay that's deep, the same amount of evaporation is going to make the shallow one very saline. And it's going to make the deep one a little bit more saline. And so then, at least temporarily, you'll have a big difference of salinity within what is technically one lake. So those are the two big things. All right, well, we have reached the halftime. So what we're going to do now is we're going to take our halftime break and come back and talk about inorganic carbon and pH. And then I think maybe two different people have asked me if we could talk more about the lab assignment that is due on Thursday of this week, a little bit more about the heat calculation. And so I would like to also do that after the break. So right now, 10-minute break. Go get a cup of coffee, step outside, pet your dog, I don't know, whatever it is you do, water your plants, kiss your children, feed your cat, I don't know, whatever it is you have to do. Go, 10-minute break. right, well, welcome back. So our next topic is inorganic carbon. And this time I'm going to give a lecture, you know, the old-fashioned way on my little whiteboard here. Now, I don't have a lot of diagrams for this. I don't have a lot of charts or pictures. And there's really just one equation. So that's kind of why we're going to do it this way. All right, so we're going to go through very orderly in this order of 8 things. So inorganic carbon. First question is, what is it? Okay, well, it is dissolved inorganic and organic carbon. And it's frequently referred to just by the initials DIC. And we'll see things referred to that way in the next 3 weeks. You know, often a 2 or 3 letter abbreviation. The first one, D for dissolved. The second one is either going to be I for organic or I for inorganic or O for organic. And then the third one will be the element. So in this case, we're talking about dissolved inorganic carbon, DIC. And you know, really, this is all of the carbon that's not in organic molecules, right? All right, why is this so important? Well, actually, dissolved inorganic carbon is important for a variety of reasons. I would say that there's really 2 or 3 main reasons. And the first reason is it's the source of carbon for photosynthesis. Right, so, you know, photosynthesis takes carbon dioxide, combines it with water, and makes sugar. That's the carbon that is the source for photosynthesis. Now, most plants and algae can only take in CO2. You know, dissolved carbon dioxide gas, you know, which is very similar to what a plant above the ground would use. If you have a plant that's living on land, it takes in CO2, the gas from the air, it dissolves in the water inside the leaf, and then the plant uses it. So, you know, regular photosynthesis really is just using straight up CO2 dissolved in water. You know, just like land plants. Now, there's some exceptions, and blue-green algae, cyanobacteria, can also use the forms of inorganic carbon that you find at higher pHs, which is to say, you know, bicarbonate and even carbonate ions. And that's really unusual to be able to use carbonate ions. And this is another one of the reasons why blue-green algae, cyanobacteria, dominate eutrophic lakes in summer. If you have a lake that's got a whole lot of photosynthesis going on because there's a lot of algae, then it actually raises the pH of the water 1 or 2 units, right, during the day when the sun is shining. And at really high pH, the form of inorganic carbon in the water is going to be not CO2, not bicarbonate, but carbonate ions. And most algae can't use carbonate ions. And then they can't do photosynthesis, right? So if, sort of ironically, if there's a whole lot of photosynthesis going on, because it consumes all the CO2, maybe that's not irony, but anyways, it consumes all the CO2, raising the pH, leaving the carbon in the water in the form of carbonate, which only the blue-green algae can use. So it's sort of yet another reason why cyanobacteria rule, in their own way. Now, what's a curious thing about cyanobacteria, you find them all over the world in all kinds of crazy environments, but you never find them in acidic water, or much, much less. So, but if it's high pH water, basic, then you can. Well, all of that leads to another big reason that inorganic carbon is important in lakes, and that is because it controls the pH. Right? Now, the carbonate buffer system that we're going to talk about in detail is what really controls the lake. It's not just the CO2, it's the whole buffer system. Carbonate buffer system. And that's pretty important, so I'm going to underline it, the carbonate buffer system, and we're going to talk about that in more detail. The carbonate buffer system, I mean, by buffer, what we mean is it resists a change in pH. It's a pH buffer. It creates a system in a lake that resists changing pH. So if a lake has a strong carbonate buffer going on, and acid rain falls on the lake won't change pH. If a lake doesn't have a buffer system and acid rain falls on the lake, the water becomes acidic. So having this carbonate buffer system keeps the pH of a lake stable and protects it against acidification. You just gotta remember that, let's see, what else do we say about this? And obviously pH affects living things, right? So pH affects a whole lot of other things, right? pH affects the solubility of metals. And if you've got acid rain and it falls on soil, it can dissolve aluminum out of the clay. And then when the aluminum ions wash into the lake, they kill the fish. Okay, it's maybe not quite that simple. There's some more steps involved, but the aluminum that's soluble at the pH causes the aluminum to be more soluble, changes form, and then it kills fish. So when you have lakes, like up in the Boundary Waters or in the Adirondack Mountains of New York State or in parts of Scandinavia, where the rocks are igneous, they're hard rock. Hard rock leads to soft water. Soft water means low carbonate. Low carbonate means unbuffered. So if you've got igneous rock in the watershed, you're going to probably have poorly buffered water in the lake because low carbonates. And that's where acidification is killing the fish. So the dissolved inorganic carbon in the water is really important, not just because it's a source of carbon, but also because of its role in the carbonate buffer system, keeping pH from changing in lakes. I'm not really sure it's like super important. Maybe it goes in the category of like interesting, but the dissolved inorganic carbon is a source of marl. Now marl is calcium carbonate, or calcium magnesium carbonate. It's not super specific. And marl is precipitates into sediments of lakes. It has some economic importance. So there are places in the United States, for example, where the soil is very old. You get south of the glacial limit and the soil was not renewed 18,000 years ago. It may be hundreds of thousands of years old. And you can have soil that's very acidic. If you're in a part of the country where the soil is acidic, then being able to add marl raises the pH and improves the soil. So in the early days of Minnesota, as a state, one of the things investigated as a source, a resource that could be sold, was marl. And the thought was, well, there's a lot of calcareous rocks here. There's a lot of lakes here. Maybe there are marl deposits. Maybe we can mine marl and sell it to southern states as a soil enrichment. And marl is a calcium carbonate, calcium magnesium carbonate, but it doesn't contain just pure calcium carbonate. It also contains other elements that have precipitated with it. So it can be a source of phosphorus as well. So it can be used as a fertilizer, a natural fertilizer. You wouldn't use this in Minnesota, where the soil is already full of calcium and carbonate and phosphorus, but farther south, Missouri, Kansas, where there's different soil types, the marl that it's just a waste here, can actually be quite valuable. So, and of course, ultimately, marl, given enough time, turns into limestone. Of course, we can't wait that long because, it takes like whatever millions of years. But ultimately, marl is what turns into limestone. Okay, so that's what inorganic carbon is and why it's important. Let's look at what forms it takes and this ultra important carbonate buffer system. All right, what forms does the inorganic carbon take in a lake? Like what, bullet point 3? 3 forms. All right, well, I think we've got forms. We got carbon dioxide. Now you could have bubbles of this, or it could be dissolved. And what we mean by a bubble is a whole lot of molecules of carbon dioxide all together, with no water inside here, just a whole lot of carbon dioxide molecules doing that gas thing, right? Picture that. There's a bubble. Carbon dioxide could also be dissolved. And what we mean by dissolved is all of those individual molecules are separated. The same number of molecules could be in the water, but if every one of them is surrounded by water, so like here's a CO2 molecule, if instead of there being a whole lot of them together acting like gas, every one of these is surrounded by water, separated from another CO2 molecule, separated from another CO2 molecule. So when we say dissolved, what we really mean is they're separated into individual molecules, each one of which is surrounded by water molecules. It's kind of a picture. Okay, so we got carbon dioxide, and that's the stuff that's in the atmosphere. It's a natural component of the atmosphere. It's like whatever, part 400 parts per million in the air by volume. And in the water, it could be bubbles or it could be dissolved. Now, when the carbon dioxide is dissolved in the water, one CO2 molecule can combine with one water molecule to form carbonic acid. So then we've got carbonic acid. Right, H2CO3. Right? H2 and one of the oxygens come from the water, and then the carbon and two of the oxygens come from the carbon dioxide. Now, this is an acid because actually when you put it in water, it doesn't actually hold on to those protons very well. It holds on to the oxygen really well, but not the protons. So it tends to break apart and into this molecule, releasing one of the protons. So this breaks apart into two pieces. This one has a negative charge, and that has a positive charge. And we say this is an acid because when you put it in water, it increases the proton concentration of the water. Now this ion here has a name. Do you know what this is called?
It's the bicarbonate ion.
That's right. This is the bicarbonate ion. Now, you'd be like, why is it called bicarbonate? There's only one carbon in it. Okay, that's not where the name comes from. I think the reason that it's called bicarbonate is that when you make calcium, you combine it with calcium, right? Calcium has a 2+ charge on it. So you could make calcium bicarbonate, but because it only has a -1 charge on it, you would need 2 of them. So if you were going to combine bicarbonate ions with calcium, it would take 2 of them for every calcium. So calcium bicarbonate has 2 bicarbonate ions. And I think that's why it's called bicarbonate. I think that's where the name comes from. Well, bicarbonate ion has a proton on it. It holds on to the proton better than the carbonic acid did, but it still can lose it. And if the bicarbonate ion loses this proton, then it becomes CO3 with a double negative charge, double negative. And you know what this ion is called? And Dolly?
It's carbonate ion.
It's carbonate ion, yep. This is the carbonate ion. And again, I think it's called that.
I think it's carbonate trioxide.
Or
is it just a carbonate ion?
I've never heard it called carbon trioxide. I suppose you could. I've never heard that though. Maybe they say that in chemistry.
It's like, it's an unstable, so it's not like a stable.
Okay, well
form.
maybe it's only stable because it's got those negative charges. So yeah, and it's dissolved in water. Like I don't care if it's not in water. It could do anything. But in water, you could see CO3, double negative, it's going to get surrounded by water molecules, right? And it's going to be the hydrogens, right, that surround it, the positive side of the water. And it can form a solid by binding to calcium. And if it did, it would only take 1 of them. right? You gotta erase that because they bond together, right? So calcium is a double negative. The carbonate ion is a double, sorry, calcium is a double positive. Carbonate is a double negative. So it just takes one to make a molecule. Calcium carbonate, calcium bicarbonate. All right, so these are the dominant forms that you see in lakes. Now, sometimes things precipitate, and what we have over here is calcium. Maybe I'll use a different color here. I don't have quite enough room to write it here, so I'm going to write the name above it. Here we have calcium bicarbonate. Here we have calcium carbonate. Now, calcium carbonate here is a typical precipitate in lakes. It's marl, the dominant thing in marl. It's the stuff that turns into limestone. It's chalk, right? Some other things, let's see, what else do we need? So, and it goes by the name of carbonate. Often people just call it that. There are some other things that you see as precipitates. So these are things that are dissolved in the water, and these are things that precipitate out, like solids. Calcium bicarbonate, calcium carbonate. Some other ones that you see are going to be dolomite. Does anybody want to guess what dolomite is? Anybody happen to know? If calcium carbonate is what becomes limestone, then what is dolomite? I'll give you a hint. It's the second most common cation combined with carbonate. What's the second most common ion? Yeah, here we go. I get the answer in here. Yep.
Isn't it like it's used in antacids, like Tums and stuff like that? So isn't that carb?
Is it calcium bicarb that's in Tums, or is it calcium carbonate?
I think it's
Okay,
calcium
case,
carbonate.
it's not dolomite. What's that?
I think it's calcium carbonate that's in Tums.
That's in Tums.
Yeah.
What is the second most? Calcium's the most common cation in freshwater. What's the second most common cation in freshwater?
Was it in magnesium?
It's magnesium. That's right. Dolomite is magnesium carbonate. Calcium and magnesium are very similar to each other. And in fact, you know, if you precipitate marl, it's going to be actually a combination of calcium carbonate and magnesium carbonate. But magnesium carbonate by itself is called dolomite. It's a slightly harder mineral. In fact, the walls of my basement here, we can look at the walls of my basement. This beautiful Minnesota rock here is probably dolomite. I was told that. I don't know that for sure, but I was told that. As a building stone, it's a desirable, it's more desirable than limestone. How about soda ash or washing soda? Have you ever heard of soda ash? Have you ever heard of washing soda? Washing soda, anyone? From the olden days, we're getting some no's here. No, okay. I think I got some over there. over my laundry room. Soda ash or washing soda is sodium carbonate. And there are natural deposits of sodium carbonate, and they obviously are used to assist in washing back in the olden days when natural products were used. How about sodium bicarbonate, like baking soda? Anybody happen to know what baking soda is? What's baking soda? No, nobody knows what baking soda is?
It's sodium bicarbonate.
It's sodium bicarbonate, right? So sodium bicarbonate. Sodium has a +1 charge, right? Not +2, it's +1. So I would assume that it's, actually I don't know that for sure, but it must be Na2, right? Somebody could look that up because bicarbs. All right, so that's baking soda. You know, and the thing is you add baking soda, you take baking soda, you add an acid to it, and then the carbon dioxide gets released. Now it doesn't take a very strong acid. I think that egg white is slightly acidic, right? But if you take baking soda and you add vinegar to it, the CO2 gets shoved off and released as a gas. If you're cooking muffins or something, the slight acidity of the other components separates the CO2, you get carbon dioxide gas. If you mix it with a powdered acid, you get baking powder. So baking powder is baking soda plus a powdered acid. I just kind of want to point out that the combination of these two, sodium carbonate and sodium bicarbonate, is a common kind of, not super common, but kind of a common evaporite, which is to say a mineral that forms on the shores of salty lakes that are evaporating. So if you've got a flat area like around the Great Salt Lake of Utah or some of these saline lakes in Africa, so you've got a thin layer of water, and in a hot summer, the water evaporates, everything precipitates, whatever's in there precipitates together. If it's a combination of sodium with the carbonates, this is a substance that's known as natron. And this is the chemical, the salt that was used in ancient Egypt to preserve the mummies. So mummies were preserved by packing them with natron. Now there's other variations on this, and one of them is called trona. And one of the early industries near Death Valley, California, is the production of trona. In fact, there's a town called Trona that's in the southwest corner of Death Valley, and they mine old evaporate salt minerals from Death Valley. I should put on my Death Valley hat. Anyways, and it's also famous as being near where the Manson family stuff took place. And according to a friend of mine who grew up near there, it's also like the meth capital of California. So it's not a cheerful place. Anyways. Okay, so we've got these four are the things that you find dissolved in water. This is the simple precipitate that we're going to talk about more, calcium carbonate. There's also a lot of magnesium ions in water. It's number 2 after calcium. So some kind of mixture of calcium and magnesium carbonates are really what you're going to get. You know, realistically, it's not going to be like a chemistry lab pure calcium carbonate if a lake makes it. But if there's sodium in the lake, whether it's down because it's downwind of the ocean or because it's a more saline lake and sodium is starting to become more dominant, then the carbonates that are going to precipitate as sodium carbonates. And these have unusual properties, including like you can make mummies out of it. Yeah. Okay, so these are the forms that we're going to talk about. And now we're going to talk about is how they're all connected to each other. Well, okay, maybe not these, but you know, how the simple ones, how these ones connect together to form the calcium carbonate buffer system. Are you ready for that? There's my eraser. All right, so these things are all connected by the carbonate buffer system. So we're going to kind of skip ahead, I think, to the processes that connect them. What number is that going to be? 5. All right. Now, I don't really have a good sense about whether you learn about the carbonate buffer system in other classes or not. I know that it's important in a variety of like apparently unrelated situations, as in like the maintaining pH in the human bloodstream. I don't know, do you learn about the pH of you learn about the pH of blood in any of your classes? So that's a good point, Keenan. So let's just take a quick little poll here. Have you learned about the carbonate buffer system at some point in your life already? Carbonate buffer system. So give me a yes, if that's a yes, or a no, if that's a no. Oh, most of the people who have responded have said yes. All right, so then let's start by having you reviewing what you know. What I want you to do is I would like you to connect those 4 things: carbon dioxide, carbonic acid, bicarbonate ions, and carbonate ions. I would like you to connect those 4 things into the carbonate buffer system. And it's a buffer system, right? It's a system, by which I mean, you know, it can go this way. These are my little arrows, right? It can go from this back and forth to this, from here back and forth to this, and here back and forth to this. So we got kind of our 3 zones here. So what I'd like you to do is try to remember what it is you've learned about the the carbonate buffer system. See if you can draw a diagram of it. You can, using the words or the chemical formulas. I'm going to have Zoom break you into little rooms of, well, how many rooms do we? You want a big room just so there's more people who know what's going on? Yeah, okay. So we're just going to have 3 breakout rooms with 4 or 5 people in a room, and just see if you can find someone who can draw and see if you can agree on how these 4 things are arranged into a system. Okay, you know, there's 4 things, so does that mean 4 minutes? Oh, a minute to pick someone to draw the picture. All right, how'd you do? Did anybody get all the way? Anybody have a diagram you want to share? All right, well, let me just show you mine. All right, so we got, let's say we got carbon dioxide gas. Right, and it's going to dissolve in the water. So now we've got CO2, and it's in the water. And it's dissolved in the water. So every one of these molecules is surrounded by a bunch of water molecules. So the carbon dioxide in the water can bind together to form carbonic acid. Right, so these two bind together to form carbonic acid. Now this is a two-way street, right? If these two bump into each other with a little bit of force, bam, then they can form this molecule. But this molecule can also break apart back into a carbon dioxide and a water molecule. It's not like permanent or anything. It's just a molecule. And if it can bind together, it can break apart. So the arrow going this way is these two things snapping together, connecting. And the arrow that way is this breaking apart. And you can take a chemistry class and calculate these rates. And, you know, I'm just going to say it's fast. Both of these is pretty fast, right? So it's like if you put CO2 in water, if you dissolve it in water, yeah, it's going to form this pretty quickly. But if you have too much of this, then it's going to shift over that way pretty quickly. So there tends to be, you know, a pretty, rational, reasonable balance of those two things. Now, one thing we said that could happen is, no, this is H2CO3. This is carbonic acid.
I think she's talking about the upper left-hand corner.
Oh, CO2.
You wrote gas, right?
Gas, yeah, there you go. I was like, that's an S? Yeah, it's gas. There we go. How's that? Gas. Yeah. Okay, so here we got CO2 gas, here we do dissolved in water. Yeah, thank you. And carbonic acid. Okay, carbonic acid, it's an acid. That means it can break apart, releasing a proton into the water. And just give myself a little more room here. Gonna make these arrows smaller. But what this is gonna break apart into is the carbonate ion, or the bicarbonate ion plus one proton. Maybe I'll make that, I'll use the other pen for that just so it's like really clear. All right. And I saw a chat flash, but then it vanished. Is that, yeah. So, all right. So here we have the bicarbonate ion. Here. This is a pretty stable ion, but it can lose that second proton. And if it did, then you would have the carbonate ion with a -2 charge and 2 protons. I guess I'm going to give a little more room here. And 2 protons. And this is the carbonate ion. Or how do you spell that? Carbonate. There we go, carbonate ion. Okay, so that's the essentially the 4 words organized in this order. And now let me try to explain to you, like my version of how does this buffer pH? I'm going to write carbon dioxide over here, just for the sake of completeness. All right, let's say that you've got a lake and it's basically dominated with bicarbonate ions. There's some dissolved CO2 and carbonic acid, and there's some carbonate ions, but the bulk of it is in the form of bicarb. Okay, so that's our lake. Let's imagine this lake. Well, let's say that some acid rain falls on this lake. And it may be sulfuric acid, right? Because it's from fossil fuel combustion, or nitric acid. And these are strong acids, which means that when you put them in water, they give up their protons and they don't want them back, right? So sulfuric acid falls into the water and adds a lot of protons. Our lake was dominated by these ions. What's going to happen? Well, maybe we need to think about what pH is, right? pH is basically the concentration of free protons per 10 million water molecules. So if you've got 10 million water molecules and 7 free protons, you've got a pH of 7. I'm saying this right? I'm saying this wrong. Okay, well, anyways, think of, I have this beautiful explanation, but I think I just said it upside down. But anyways, pH is basically about the concentration of protons, right? If we have, a pH of 7 in this water and a pH of 7 in this water, they have the same pH, but this one has more total free protons. It's all about the concentration of free protons. And the thing about pH is that water is a molecule. It's above absolute zero. It is not stationary. It's moving, it's vibrating, it's spinning. The atoms are going back and forth within the water molecule. And there's kind of like a distribution of how fast they're moving. At any given instant, some of the protons are close to the oxygen. At any given instant, some of the protons are far from the oxygen. At any given instant, some of the protons are moving faster than other protons. And you got a lot of water molecules in a bucket of water. At any given instant, some outlier protons, the ones that are just at the far end of the distribution, are moving too fast and break free. Because there's so many water molecules, right? So at any given instant in time, if you get a bucket of water, some of those water molecules are breaking apart into protons and hydroxide groups. Now, water is a very stable molecule, and the vast majority of them will be solid H2Os. But at any given instant, some will be breaking apart into components. Now, if a proton meets a hydroxide ion in the water, boom, they'll convert back into water. And okay, you know, it's probably not like literally an isolated proton roaming around, right? It's probably actually attached to another water molecule. So, you know, really it's probably an H3O, blah, blah, blah. I know for some chemistry people, that's like their pet peeve, right? These are probably not like completely perfectly isolated like I've drawn. They're probably associated with the water molecule in some kind of like loose association. Okay, you know, you could get more realistic about it. But the part that you need to know is that any given instant, some tiny fraction of the water molecules will be broken apart like this. What fraction? Well, ordinary water sitting around at the surface of the earth, ordinary temperature, ordinary pressure, what fraction of the water molecules will be in this kind of dissociated state? Pure water, pure, no contamination of any kind. What fraction will be dissociated? Does anybody happen to know? I think you're just going to go duh when I tell you. So guess. Yeah, no, it's equilibrium. Yeah, very close, Keenan. Very good guess. The answer is 1 in 10 million. 1 in 10 million, right? What is 10 million? Well, a million is 10 to the 6th, right? So 10 million is 10 to the 7th, right? 1 in 10 million. And that's where the 7 comes from. Now, let's say that you increase the concentration of free or loosely held protons in the water. Like, let's say you increased it 10 times. Then instead of being 1 proton for every 10 million water molecules, if you increase this 10 times, it would be 1 for every million. If you increase the concentration tenfold, so instead of being 1 for 10 million, it would be 1 in every million, then that would be a concentration of 10 to the 6th. In other words, pH 7, pH 6. Let's say, on the other hand, instead of being 1 in 10 million, you reduce the concentration by 1/10. Like you remove 9 out of 10 of them. 9 out of every 10 of them. So you reduce the concentration to 1/10 of what it was before. Then instead of 1 in every 10 million water molecules, it would be 1 in every 100 million. Okay? Well, 100 million is 10 to the 8th. So then you would have a pH of a concentration of 1 out of 10 to the 8th. In other words, a pH of 8. Okay, so this is what pH is. pH is the ratio of free protons to water molecules. It's like parts per million, parts per billion, you know, something like that. And the number, pH 7, pH 6, pH 8, whatever, the number is the exponent. So if you increase the proton concentration by a factor of 10, you're going to decrease the pH by 1 unit. If you decrease the proton concentration by a factor of 10, like you go from here, if you decrease it by a factor of 10, no, sorry, did I say that backwards? Yeah, anyways, okay. I'm making it less clear by explaining it more. Okay, so this is what pH is. pH is about the concentration of protons, and it's really about the ratio of protons to water molecules. Water, if left alone on its own, will dissociate, creating a pH of 7. When you add an acid, you're going to raise the concentration above what the water would normally naturally have. If you add a base is a thing that takes protons out of solution. If you add a base, it's going to remove protons. It's going to decrease the concentration of protons. So it's going to, increase the denominator, and it's going to raise the pH. Okay, that's pH. Now, I know you've learned about pH before, many times probably. And you've probably learned about it in much, much more, correct terms. But I also know that some of you, even though you have learned this much more correctly, didn't actually understand it because it was like just too much detail. So this is the detail you need to be a limnologist. Okay, and to understand the carbonate buffer system. Okay, any questions about this or any corrections? Did I say anything wrong? Because like sometimes I talk too fast. And yeah? What do you say? Okay, so let's say that you add an acid, and an acid is a chemical that when you put it in water, increases the concentration of protons. It's a proton donor of some kind. So let's say we got some natural water, and most of the inorganic carbon is in this form, and there's a lot of it, and you add protons. What's going to happen? If you add more protons, then in any given instant in time, a bicarbonate ion has a higher chance of bumping into a proton. If a bicarbonate ion gets too close to a proton and they're not moving too fast, right? Not too fast in the wrong direction. If a bicarbonate ion gets too close to a proton and they're not moving too fast, boom, they'll stick to each other because one's positive and one's negative. They stick to each other. Oh, and now you've got carbonic acid. The higher the concentration of protons, the more frequently those interactions are going to happen. If the concentration of protons goes up, the rate of this reaction will increase. And in fact, you can just keep adding protons, add acid, add acid, add acid, add protons, add protons, add protons. But all of those protons are going to stick to the bicarbonate ions and become carbonic acid. And then those protons are not in the water anymore. And if the protons are not in the water as protons or loosely held, by hydronium ions or whatever, then the pH doesn't go up. So that's how this functions as a buffer system. If you're dominated by bicarbonate ions and you add an acid, it's just going to shift form, essentially sopping up, sponging up, absorbing the protons. And if there's no free protons, then the pH doesn't change. There's no change in the concentration of protons, no change in pH. Same thing's true if the lake was dominated by bicarbonate ions. Now, the lake's going to be dominated by, did I say that wrong? The lake is going to be dominated by carbonate ions if there's very few available protons. Because if there's any available protons, they're going to bind to the carbonate and form bicarb. They're going to form bicarb. So you really only get a lake with a high concentration of carbonate ions. That only is going to happen if there's not a very high concentration of protons. If there's a high concentration of protons, it's going to shift over this way. So when a lake has a very high pH, meaning a low concentration of protons, it's going to be dominated by carbonate ions. If a lake is very acidic, meaning there's lots of protons, then all of the carbonate will be converted to bicarb. And well, frankly, all the bicarb is going to get converted to carbonic acid. So a very low pH lake is going to be dominated by carbonic acid. A neutral lake will be dominated by bicarb ions. And a high pH lake is going to be dominated by carbonate ions. In any of these conditions, like if you added an acid to a lake in this state, then you could add, it's like you're adding a lot of protons, but all that's going to happen is those protons are going to vanish from the water because the carbonate ions are going to bind to them and convert to bicarb. And until that's done happening, you can add as much acid as you want, the pH will not change. Or if you had a lake in this condition and you added a base, the base might absorb the protons. Well, what's going to happen? If you absorb all of these protons, then you're going to prevent this interaction from happening. And then all you're going to get is carbonic acid splitting apart and never getting back together again. So if you added a base to this lake, sure, you might remove all the protons. Well, what's going to happen? Carbonic acid is going to split and restore the proton concentration. That's how it functions as a buffer. Okay, now, like I said, it seemed like most of you had learned about this before. Hopefully this has helped you remember what you learned before, or maybe just replace it with something you understand. Ideally, in a chemistry class, you learned like, you know, math and stuff, and you'll find a way to connect the limnologist's view to the more correct, sort of precise, calculatable chemistry perspective. But at least learn the limnology view. Okay, so this is the carbonate buffer system. Obviously, it's pretty important. The textbook has, you know, whatever, like 4 or 5 pages, 5, that's it, on the carbonate. So it's all inorganic carbonate, and I think like 2 out of 5 of them are on this one equation. So obviously, I really want you to understand this, to remember it and understand it and be able to explain it. Now, the last step is carbonate precipitation. And let's think about this one over here. Now, carbonate and bicarbonate ions are the dominant anions in lakes. But at any given moment, there are also going to be calcium ions and magnesium ions, right? Now they're going to be dissolved in the water. I'm gonna draw some water. Let's see, this is positively charged. So this is going to be surrounded by the water with the oxygens facing it. The oxygens are slightly negative, so the water molecules rotate. So the slightly negative side is attracted to positive ion, right? And the reason that this is kind of stable, the reason that we talk about calcium carbonate dissolving in water, is that if the negative side of the water is facing the cation, the positive side of the water molecule is facing anions. So this is kind of stable, having a mixture of positive and negative ions dissolved in the water. Let's say that we have a lake at this high pH, and then all of a sudden, we pull all of the protons out of the water. Now, what do I mean by that? Well, photosynthesis consumes carbon dioxide, right? So if you've got a whole lot of photosynthesis going on, like a bright sunny day and a eutrophic lake and a thick, cyanobacterial layer, a thick blue-green algae layer, right? Crazy photosynthesis going on, right? Photosynthesis consumes CO2, pulls it out of the water. what's going to happen? Well, the carbonic acid is going to break apart back into CO2 and water, because this is a pretty quick reaction. So that gets pulled that way. This is also a pretty quick reaction. So if you remove this from the water, it's going to pull this over, and that's going to pull this over. That's going to pull protons out of the water. If you're pulling all of these protons out of the water, and this reaction is kind of slow, there won't be any protons here. Now, if you had a lot of extra protons here that were occupying the water molecules, the attention of the water molecule, right? So the water molecule has a positive side and a negative side. And if you've got extra protons in here, you know, they could be floating around. If you pull all of those out, and suddenly what you've got is a weird disequilibrium where you've got lots of negatively charged carbonate ions, doubly negative, in the same water. And if there is positively charged calcium or positively charged magnesium, these things are going to get together and precipitate. If you pull the protons out of the water when it's at a very high, so it's a very high pH, and then suddenly you remove all the protons, making it a very high pH. I'm sure that's a clear explanation. Anyways, what you're going to get is precipitation of calcium carbonate. This is marl. This is whiting. And this is a precipitate. It forms little flocky snowflakes. It's a solid. It drifts down through the water. And it's a really important event when it happens. A whole lake can just suddenly turn gray or white. I mean, they say white, but it's not really white. It's kind of gray. Just like, you know, lake, it's green, blah, blah, blah. And then suddenly, wow, it's kind of weird gray color. And this stuff sinks to the bottom of the lake and just takes everything with it. These sticky little clumps of calcium carbonate flock drifting downward. And anything near it sticks to it and gets carried down. Yeah. Well, that's the end of the calcium carbonate buffer system with the precipitation, sorry, the carbonate buffer system with the precipitation of calcium carbonate. And this kind of happens because the carbonate is trapped here because these reactions are not all like instantaneously super fast, whereas photosynthesis can be really fast. Okay, well, looking at the clock, obviously I think this is a great, weird subject. Just a second. What's going on out there? Oh, it's rain. Okay. Some other things that I would want to say about this subject. What I want to say about it. What is it that affects the distribution of these elements in a lake? Well, obviously, you know, precipitation, chemical precipitation, and the transformation among these different forms controls them. CO2, to go to the subject of what controls the concentration of these things in a lake. Here's my lake. Obviously, you know, these three things are all happening in the water. You can have diffusion of CO2 out. Right, if there's a lot of decomposition going on, CO2, if it's greater than the solubility maximum, can diffuse out. If the CO2 is totally consumed by photosynthesis, it will diffuse in from the air. Within the water itself, obviously the CO2 goes into organic matter because of photosynthesis. And it also goes back by respiration. Photosynthesis and respiration, photosynthesis and respiration are fast. And you know, bright sunny afternoon, in a matter of an hour, they can suck all the CO2 out of the water, raise the pH by a unit or two. Sun goes down, photosynthesis stops, respiration just keeps chugging along, and the pH will gradually rise back up again. So just in terms of like moment to moment, hour to hour, photosynthesis and respiration are what control the pH of a lake, the carbon dioxide concentration, and therefore the pH. Longer term, you know, it's really more about, do you have calcium and magnesium in there that enables the carbonate and bicarbonate to stay in solution? You know, is there alkalinity or not? Let's see, diffusion to and from, photosynthesis and respiration. And of course, you know, chemical precipitation takes this inorganic carbon out of the lake. That's our chemical precipitation line. But then at the bottom of the lake, the pH may be very low, it may be acidic. There may be other things happening in here, and it may actually redissolve. So here's chemical precipitation, not rain. And then here we can have dissolution. Calcium carbonate is a funny mineral. It precipitates easily and quickly, but dissolving it again, unless it's very acidic, is actually pretty slow and gradual. So a lot of times the calcium carbonate that precipitates to the sediment stays there forever. And it can form actually little white layers in the sediment as the sediment accumulates. And there are lakes in which you can count the tree rings, count the annual layers of the sediment, because every year in midsummer, there'll be a lake whitening event and there'll be a layer of calcium carbonate, a layer of marl, and then more brown organic matter. And then the next summer, a layer of marl. I'll show you a picture of this, I suppose, next week. There's a picture, the last picture in this chapter is a picture of a gravity core, a sediment core from Lake Zurich, showing these layers. So be sure that you take a look at it. I want to show you one last picture here before we talk about the lab. I just want to show you you can see this. This is Lake Natron in Africa. It is a beautiful lake. And, okay, let's go to the next one. It's famous for pink flamingos because of the very salty water. There are very few things that can live there, but one of the things that can is pink. So here's the lake when it's dried out. Here's a beautiful shot of the lake drying down and the salt deposits. And there's flamingos in the distance. These very saline lakes, especially if they're sodium carbonate type lakes, are often pink with pink deposits because of the algae and crustaceans that live in them and the brine shrimp. And this is what makes pink flamingos pink. Just wanted to say that in case, I missed that at some point during the semester. I had to show you like a really pink lake. And these are pictures of Lake Natron in Africa, which is in the lake. Okay, just wanted to share that with you. Now I will stop sharing. All right, do you have any questions about salinity or dissolved inorganic carbon? I think I've said most of what I wanted to say. And I think almost everything I've said is also in Calf. Everything I didn't say is in Calf. And you have reading questions directing you to it. But any questions? Did this help you understand pH and the carbonate buffer system, I hope. Okay. Obviously, you know, we're not going to do calculations with this. What I really want is you to be able to understand it and explain it. Yeah. Okay, that's what I want to say about the salinity and carbonate. That's what I have time for. So now I thought I would just perhaps answer questions that you have about the lab for the calculation of heat, the heat lab thing. Okay. I know what I need to say. Lab on Thursday of this week will be on campus in 2 lab groups, 1 o'clock and 2:30. Unless you contact me, I'm going to assume that you will come to the same lab group you did before, either the early or the late, the 1:30 or the 2:30. We will be on campus. We're going to look at the water samples that we collected last week. A couple people joined me at the lake. It was very pleasant. And we collected algae and water samples. We're going to look at the algae. We've got zooplankton samples that we collected earlier in the semester as well. So that's what we're going to do. And I think there will not be any calculation for the next lab. So yeah, I really need you to say that. Okay, any questions about the schedule this week? Will I see you on Thursday? All right, and Dolly.
So where in the campus? So which room?
Oh, come to the Science Education Center. I'm pretty sure it's going to be room 214. I'm not sure of the exact room number, but it will be Science Education Center. I will post the room on D2L.
Okay.
It'll either be the second floor or the first floor.
Thank you.
Yeah, good question. Thanks for asking. Okay, other questions?
Yeah.
What if we, no, go ahead. You go.
No, I was going to talk about the lab, so you go ahead.
Oh, I was just going to ask, what if we don't remember which lab group we were in before?
I think I posted it on D2L. Look through the D2L announcements.
Okay.
Yeah. And I mean, I think it's okay if like one person goes to the wrong lab, but you know, because of the room limits, we have to keep it below 12, I think, at a time. Check the D2L announcement and see. Okay, other questions, comments, questions? Jude.
Yeah, so for lab 7, I had trouble, well, I calculated a final temperature, but it seemed way too high. So I think I did it wrong.
Well, obviously, if you mix ice into water, it's going to lower the temperature of the water.
Yes, I must be doing something wrong then.
So the temperature needs to go down. Right, so the water under the ice is above freezing. You're going to pull heat out of the water to melt the ice. So the temperature of the water will go down. But how far? Well, it depends on how much heat you pull out of it and the specific heat of water. Does that help? So it could be that you calculated the amount of heat, but then instead of subtracting it from the water, you added it to the water.
So I guess am I using the right equation to find out the final temperature? I'm using the one where it's like energy equals mass times specific heat times the change in temperature. Is that the correct equation?
Yeah.
No?
Yeah. So the energy, that's how much energy, how many joules, how many calories got taken out of the lake water. And then if you take that much heat out of the lake water, what will the change in temperature be? That's the equation you're describing.
So the energy won't be the energy that takes to melt all the ice off. It'll just be the energy that's coming from the water.
Yeah, because some of the heat some heat came from the sun. So it's like this, you've got the lake, it's got ice in it. Sunlight comes down, so the sun adds heat, right? And now you've got the same lake with thinner ice. And then the wind breaks up the ice, mixes it into the water. So there's going to be heat that comes from here, from the liquid water, and is going to go into the ice to melt the ice. And then you've got the whole thing is liquid. So you start out with, here's our ice. How much heat would it take? How much heat will it take to melt this ice completely? Then a certain amount of that energy comes from the sun. And then whatever energy didn't come from the sun must have come from the water. And so if you take that much heat, if you take this much heat out of the water, what's the, of course it's going to melt the ice, but gaining, the ice gains heat from the water, which melts the ice. The water loses heat to the ice, and losing that heat cools the water. So you're kind of transferring heat from the liquid to the ice. And you could use a capital Q for heat if you wanted. You know, here's heat from the sun, and then heat from the water. So you really only need, in terms of like physics, you're only using two equations, and those equations are both just the definition of specific heat, and the definition of the heat of fusion, or the heat of melting, right? So there's two equations, and they're both really just definitions: the definition of specific heat, and the definition of the heat of fusion. Those are the two equations. And then you need to know how much ice you're talking about and how much water. That's just geometry. What's the volume of the ice, or what's the mass of the ice, and what's the mass of the water? And then you need to know how much heat comes from the sun, and I think I gave you that number. So it's kind of like there's maybe 5 little pieces. None of them is that hard, but I think the hard part is fitting all of those pieces together. I could be wrong, but I don't think any of those pieces is particularly hard. The sunlight, adds energy. Is that helping at all? I don't know.
Yes, it is a lot. So to calculate the amount of heat that came from the sun that's melting the ice, would I multiply the 26 millijoules with the surface area of the lake?
What was the 26 millijoules? I don't have it handy right here. Is that the
amount of energy from the sun daily?
Okay, all right, thanks, Keenan. I see it. Yeah, so that's the amount of sun per square meter per day. So you could do it 2 ways. One is you could calculate the total volume of ice, the surface area and so on, or you could take a typical square meter, which involves more like visualization but less calculation. Yeah. But yeah, so how much heat does the lake absorb? Well, there's so many kilojoules per square meter per day. There's so many days, so many square meters. That's the total amount of heat. Does that answer the question?
Yeah, I think I'm just having a tough time with the calculations. But I'll shoot you an email if I'm
You
so
can,
confused.
you can give that a try. Yeah.
Yeah.
Yeah. Other questions? I think Desiree was asking when 3, 4, 3, and 4, the ones that were group labs are going to get graded. I think that's 3 and, oh, it is 3, 4, and 5. Those are now near the top of my grading list. Typically Friday is my grading day, so I have to say probably Friday. There were fewer of them to grade, so you'd think that would be quicker, but the calculation kind of takes a flat rate amount of time regardless. So probably Friday. Other questions? Abdul, you all good? Yeah, okay. All right, people, I guess that's it. I will see you all on Thursday, unless you're in my other class, in which case, I'll see you tomorrow.